Hello, everybody. Welcome back to part 2A of my homework 2. In this part, I'm going to explain and code the secant and Newton methods for finding the roots of a scalar one-dimensional function. So, I think there's really, the root of a scalar one-dimensional function, what is that? Well, normally if you ask me to find the root of a scalar one-dimensional function, I just take the derivative and find when the derivative equals 0. That's what we've been taught since, Calc 1. But that's not really going to work that works fine, but we're going to use a couple other methods for finding roots of a function. And roots are, of course, really important. And these methods might be a little bit easier to do for a more complex function, or a function where we don't actually understand where you don't understand the function itself. You can only guess points. That's another strength of the secant and Newton methods. And for this first part, I'm just going to be focusing on a scalar one-dimensional function, so it should be pretty simple. I guess with all that said, let's go ahead and get into the secant function. So, secant method. This is the Wikipedia page for the secant method. For numerical analysis, the secant method is a root-finding algorithm that uses a succession of roots of secant lines to better approximate the root of a function f. The secant method can be thought of as finite difference approximation of Newton's method. Ooh, that sounds familiar. It's because it's right here, and I'm going to do it later. However, the secant method predates Newton's method by over 3,000 years. So isn't that cool? Anyway, let's explain graphically what secant's method is doing. So secant's method is going to start out with 2 points. Let's say x0 and x1. And so you have x0 and x1, and you can evaluate those at function. So you can get like an f of x0 and then an f of x1, which I'll just call f0 and f1. Then you can find the straight line between those 2 points. See, this red line is f of x, the blue lines are straight lines. So then you would find the straight line between those 2 points, and you could find the x-intercept of that, and that would be your second guess. So then you would take your second guess and your first guess, and you would go up and you would find a new point on the function, and then find the tangent line between those 2 points, and then not the tangent line, but the line connecting those 2 points. I'll talk about tangent lines later, so that's why I messed that one up. But you will connect, you'll take these 2 lines, find the slope and the intercept between them, and use that to guess a third point. Then you'll take the line between you'll get your third guess, and you'll find the line between your second and third guess, and slowly you will edge your way towards finding the actual intercept, which I guess in this situation is like right here where my cursor is. So with all that explained, let's look at the derivation a little bit. For finding a 0 of the function f, the secant method is defined by a recurrence relation. So you're going to kind of iterate through this method, keep guessing new xn's and xn minus 1s, all that, or not guessing, but keep calculating new ones until you find a very small difference between the calculated root and 0, as this is saying right here. So if you take a look at this, it's saying that your xn, so your next guess, is just your previous guess, times f at the function at your previous guess, times, and this is just the slope, or minus that, times, this is just the slope. So this is like run over rise. Well, wait a second, is that? Yeah, this is the inverse of the slope. I don't know why it's written that way. But, well, actually, no, it's written that way because of the way you would have to shift it around. But anyway, you can kind of imagine how this method works graphically, and I think the derivation is pretty simple once you understand it graphically. So hopefully you're able to follow along with my graphical representation. Apparently someone 3,000 years ago knew how to do it. So I wonder who knew how to do this 3,000 years ago, because Newton certainly didn't. And whoever invented, I don't know who invented the secant method, but I doubt that person was alive 3,000 years ago. So anyway, I went ahead and imported some additional things, Jax NumPy, and changed the config of NumPy, or of Jax. And none of that is important for this problem, but it will be important for Newton's method. And so let's go ahead and take secant and Newton's method. So I already did the imports. Let me go ahead and write this secant function first. So I want to define secant And what do I need to give secant? Well, I kind of talked about it earlier. It needs some function f. It needs two initial guesses, an x0 and an x1. And then there's a few things I need just for the programming the function. So I'll give it an f. I'll give it two initial guesses, x0 and x1. And then I'm going to give it a couple of values that are for the way we're going to solve it. First, I want to give it a max iter. So I want to give it some value. I'm going to iterate through secant's method, right? And I want to give it some maximum values just so it's not going on forever, getting an error. And I'll go ahead and maybe say that's 50. I could set it to 100, but the professor said 50 when he did in class, so I'll just go with 50. Now, sorry. In addition to max iter, I also am going to need some tolerance value, because I need to check these values of x and see what's the difference between the function evaluated at x and 0. It should be very, very small, but I need to sort of go through this value and check every value of x using this sort of tolerance. So the way I'm going to do that is by defining tolerance as a very, very small number. And I'll go through and have like an if statement at some point saying like if the value is below the tolerance, then we'll break out of the loop. So I'll say the tolerance is 1 times 10 to the negative 10th. And so with that, what do I need to return to secant's function? Well, or what do I need to return in the secant function? Well, really the final value I want is this final value of x, like the final guess of x. So I'll go ahead and call that xn for now, even though xn probably isn't what I'll end up calling it when I code out the function, but whatever. So we have sort of the framework for the secant function. What do? Well, going back here, I said that I start out with 2 points, x0 and x1, and then I evaluate them at the function, so f of x0 and f of x1. Well, that's pretty easy to do, so I can go ahead and do that now. So I will just say that f0 is going to be f evaluated at the initial guess, x0, and then f1, similarly, is just going to be f evaluated at x1. Great. So now that I have those two, where should I go from here? Well, I think from here I actually want to try to go into a loop. So I'm going to say for I, just for some iterable, in a range with the length max iter. So just saying for I, basically from 0 to 50, I want to look at some values. Specifically, I want to calculate a new guess every time and then check that guess to see how close it is to 0, similarly to what I explained earlier. So how do I calculate x2? Well, Wikipedia told me how to calculate x2 over here, right? This is sort of the function. So I'll go ahead and probably type this into, I guess let me do it for one step, and then I think that'll make it easier to explain later. So for I in max iter, I want to go through and do this for one step. So I will say that x2, so my next value of x after I've done f0 or x0 and x1, my next value of x is just going to be x1 minus f, I believe it was f0, right? Yeah, so f of x n minus 1, so that would be f1 in this case. And then that's going to be multiplied by the run over rise, or the inverse of the slope. So that is just going to be xn minus 1 minus xn minus 2. And so that would be like x1 minus x0. So x1 minus x0, or the run. And then on the bottom, I just want to do the same thing, but for f1 and f0. So f1 minus, I'll put it like that, yeah, f0. Pretty sweet, right? So let me put a space in here. I just like to have my formulas look good. So yeah, this is x2. So now I've gone through and calculated x2 when given the initial points 0 and 2. So if we were looking at this chart, I'm here at x2 right now. Well, what do I need to do from x2? I need to I need to find f at x2, and then if that f of x2 isn't too close to 0, then I need to make another line similar to what I've just done. So let's go ahead and maybe say, what is f2? Well, f2 is just going to be the function f evaluated at x2. Now I want to check and see how close I am to 0, because if f2 is 0, then I found the root and I just got really lucky with my initial guesses. So I'll go ahead and say that if the absolute value of f2 is going to be less than tolerance, or tall, I should say, just tall, then if I do that, then I should break out of the loop, right? So this is all fine and dandy, but what if f2 is less than the tolerance? Or what if f2 is greater than the tolerance, like it is on this graph right here? Well, in that case, I would want to find the line between f2 and f1, right? Or the point x2 and f2, and the point x1 and f1. So I can actually go ahead and just change some of my variables real quick and go through the loop again. So I'll go ahead and maybe redefine x0 is now just going to be what was x1, right? And then x1 is just going to be what was x2. So I'm putting this x2 back in as a new point. And similarly with f0 and f1, I am just going to say that f0 is now f evaluated at x0, the new x0, and then f1 is just going to be f evaluated at the new x1, right? And so now I've reset my variables, and now I'm free to iterate back to this x2, solve for f2, find if there is any difference, and now I can sort of iterate through this, and it'll just keep doing sequence methods until eventually we reach this condition. The absolute value of f2 is less than the tolerance, so the value of f2 is very, very close to 0, and then it'll break out of the loop. So with that, I want to go ahead and return x2, because that's the final guess. So that would be the x value of the root of x, or of the function f. And so now I can go ahead and run this function. Pretty sweet. So where do I want to go from here? Well, from here, I want to probably generate some function f of x, and then check it and see what it is. So I'll go ahead and define f in terms of x, and that is just going to return some function I want to look at. So I'll just say that function is f, or wait, no, that's not it. The function it's going to return is just going to be like maybe x minus, we'll say x plus 0.3, so there's a root at negative 0.3, times x minus 0.2, and so there's a root at positive 0.2, times x minus 0.8. So there's a root at positive 0.8. So I can go ahead and run that, and then let me maybe graph the value a little bit. You know, I'll do that in the next cell. So I'll maybe get a list of x values, and I'll just use np linspace to do this, right? And so I will maybe go from -1 to +1, and I will have maybe 50 values. And then I'll say I have a y list, and that y list is just going to be f evaluated at the values of x list. So I have a bunch of x values, I have a bunch of y values. Now I can just I can make a subplot. But how do I do that? I say, sorry, I forgot, I blanked for a second. Make subplots, and then I run that, and I shouldn't have run it yet because I need to add the scatter to the subplot. So I would just say the x is x list, and then the corresponding y is going to be equal to y list. So that should all run. Yeah, sweet. So this isn't a great chart. I should probably maybe start at -0.5, and then going to 1 looks alright. Let me see what happens when I do that. Yeah, so now the roots are pretty apparent. This is x equals 0. You can see there's a root at approximately -3, or -0.3, and then there's a root at approximately 0.2. Well, I mean, there's a root there, but you can kind of tell it's at approximately that value. And similarly, there's a root at 0.8. And this is the function f as I defined it. So now, as this problem asks for, I have a scalar one-dimensional function. Let's use the secant method I programmed out and see what secant method gives me. So I already defined secant as a function. Let me go ahead and get rid of this graph for now, just so I can see more of my typing as I go. And I will say that secant, well, what does secant need? It needs an f value, so I will say that f is just f, except it's not capital, it is f equals f. And then I need to give it some initial guesses. Well, these initial guesses are pretty flexible, honestly, but I'll go ahead and maybe say, actually, I'll just go ahead and define these initial guesses within the function. I'll say that x0 is just going to be, let's just say it's -0.1, and then x1 is just going to be positive 0.1. And so those are my two initial guesses for the roots of the function. So let's see what my secant function gives me when I run it. Well, the secant function returns to me 0.2 approximately. You know, it's a little bit less, but that's just because of the way I set my tolerance up. So, is this correct? I believe it is, because we know f of x has a root at 0.2. So one of the problems with secant function is that secant function will only give you one root back. Even when there's more than one root, secant function only returns one root, which is kind of, not great. And the way I'm going to do Newton's method won't be any better for this, but it works. And gets the job done. So I have this f of x, my scalar one-dimensional function. Let's go ahead and talk about Newton's method for a second. So what is Newton's method? Let's scroll up to the top of the Wikipedia article. Newton's method is a root-finding algorithm which produces better approximations of the roots of a real value function. The most basic version starts with a single variable function defined for a real variable, the function's derivative, and an initial guess for the root of f. And you can go through and do some other things, and this is sort of the function we're going to program in. But let me come down here, and this is a great chart for explaining Newton's method. So I start out with some guess at xn, and then I evaluate it at fn. So f at xn, or I guess like some initial guess, so f at that 0. Then I will find the derivative of said function, and in this case I will use Jax's gradient to find the derivative of that function. And then what I can do is I can look at where that derivative intersects 0, and then I can check to see, is this close to the actual root of f of x, similar to what I did before with secant function, or with secant's method. And if that doesn't work, then I can go ahead and evaluate it at another point. And what you're going to see is that the tangent value will slowly snake down to a root. Or it'll sort of make its way down to a root gradually. It'll sort of arc its way down and do whatever. This one, is this animated? Oh yeah, this is animated. Cool. So you see you get one root, and here's the second root. So now you're going past it a little bit, but you can circle back around, you get another root. You can take the tangent line, find the intersection, and now you are basically, very, very close to the tangent of the function. And I think maybe this is in German or something. Function tangente. I don't know, maybe it's just someone who doesn't know how to spell and spelled it phonetically. It looks like English words, but just spelled wrong. But phonetically it sounds the same, so that might be in German, but I'm not certain. Anyway, let's go ahead and work on programming out the Newton's method. So I'll go ahead and define Newton. And what does Newton need? Well, similar to before, I need to give it a max iterator, because I am going to iterate through and do the method a bunch of times, and then a tolerance. So I'll just use the same ones I defined earlier. But what else does it need? Well, I still need a function to evaluate, obviously, and then additionally, I only need one initial guess. So that is Newton's function. Similar to before, I'm just going to return x2, the final value of that I find, or my final guess, which will just be, I guess it'll be x1 in this situation because I only need to do one guess. So how do I go about getting Newton's method? Well, I can go ahead and going up here, if I just started out with x0, right, and I wanted to get my next guess, I would say I get x0, I evaluate f at x0, and then I take the derivative of f and evaluate that at x0. So let's go ahead and maybe try to program this in a little bit. So I will go ahead and maybe say that f0, or the function evaluated at x0, is just f evaluated at x0. So then I can go from there, and I can maybe find the derivative of f. So f prime is how I will abbreviate that. So how can I get f prime? Well, earlier I mentioned as I began the video, I imported JAX and JAX NumPy, and that was something I mainly did for the next part. I think part 2b will really need it. But let's go ahead and find the derivative of f by taking the gradient, or find the derivative of f by taking the gradient of it. So that's just going to be from JAX. We will use the gradient functionality, and I will say take the JAX gradient of f. So then that is just the function for the derivative of f. And in fact, if I were to go ahead and maybe run this in another cell, let's see what I get. It runs, so then what is f prime? That's just a function, and it's a function based on f of x. So if I maybe go ahead and evaluate f prime at 0, I would I would get an integer error because I believe it needs to be 0 with a decimal point to prove it's an integer. And this tells me that the derivative at x equals 0 is going to be negative 0.4. Well, if I go ahead and pull up this chart of f again, at 0, does it make sense that the derivative is negative 1 or negative 0.14? It does to me because it looks like the line is decreasing by a little bit, not much, but by a little bit around there. So that number makes sense to me personally. So with that, I'll get rid of this graph again, and I think all this stuff checks out in my book at least. So this f prime is just the derivative of f. So then I can start my loop up again, and I can say for I in the range of max iter. So in the iterable range, I want to, well, what do I want to do? I want to evaluate x1. So I will just say that x1 is going to be equal to x0 minus, and it is, the function divided by the derivative of the function. So that will just be f0, or the function evaluated at x0, divided by f prime, so the derivative of the function evaluated at x0. Pretty cool, right? So now I have this iterable, but while I'm iterating through this, I of course need to check x1, or specifically check the function evaluated at x1 to see is that the root. So I will do that. I will say that f1 is going to be equal to, if I can spell, or if I can type, the function f evaluated at x1, the x value I just found. And then similar to what I did for what I did up here, I can say that if the absolute value of f1 is less than the tolerance, then break out. But if the absolute value of f1 is not less than the tolerance, what do I need to do? Well, I need to go back and set x1 equal to x0 and evaluate f at x1, and then sort of run this function over again and get a new guess x2. So what I can do is I can just say that x0 is now going to be x1, and then on top of that I will say that, what do I need to say? I need to say that f0 is now f evaluated at the new first guess, which in this case would be the x0, which would be the x1, which is what I calculated from x0, which was my true initial guess. And so now this loop can just keep going, and I can iterate through it over and over again and get the Newton's method. So if I go ahead and run that, it will not run with any errors, so that's a good sign. So now I can maybe just take Newton and say that I want to evaluate the function f. And what should my initial guess be? Well, let me give something close-ish to one of the roots, so that way I'll say that my initial guess is maybe negative 0.5. So negative 0.5, right? Because one of the roots should be at negative 0.3, so that should probably lead me to the root at negative 0.3. Let's see what it gives me. It's running, and okay. So it's returning an array of x1, and that array is just something it's returning because I'm using the Jack's gradient. It has to return this array. But the value I got here isn't exactly correct if you look at it. You can see that, yeah, I should be getting a value, you know, at negative 0.3, right? That's what the root of this function right here tells me. But instead I'm getting like negative 0.36, which doesn't really entirely make sense. Now, I think that might be because of my initial guess, potentially. It could be because of my max iteration. So let me maybe set that to 100 and see what happens. Nope, I get the same result. So maybe if I try a different initial guess, maybe negative 0.4, it'll go ahead and calculate it again. And now I'm getting a final value that's closer, but still not actually correct. So that is kind of weird. This is a weird one. I didn't get this error when I was practicing it. Well, let's go back and let's think through this again. I take f evaluated at 0, and then I get the derivative of f. So then what I'm going to do is I'm going to take the variable x1, and I'm going to evaluate it at this formula it gave me before. So f evaluated at x0 divided by the derivative evaluated at x0. Is that what I've done so far? Yeah, it's right so far. Maybe I'll put this in parentheses, but that shouldn't make a difference. That just makes it a little bit more clear to me what's going on, but that shouldn't affect the computer. And then I go ahead and I say that f1 is just f evaluated at x1, which also makes sense. And then I will say if the absolute value of f1 is less than the tolerance, so it is a less than, right? Yeah, and tolerance is a really low value, then it'll break out of the code. But if not, I will go ahead and say that x1, I'll go ahead and say that x0 is now, x1 is now x0, and the f evaluated at x0 is just that. So, I was expecting this to work. Let me try running this one more time. This is really weird. If I try a different value, maybe say a positive initial guess, so let's maybe say that I want to target this root at positive 0.2. Maybe I'll say my initial guess is x0 at 0.3. What do I get? Well, now I get a value that's pretty close, but not really all that close. Maybe if I take the tolerance down a little bit more, I'll get something good. Not really. Maybe if I just go really low, will this get me any closer? No, it won't. It keeps not getting me where I want to go. Is this f correct? Am I running f correctly? Yeah, I am. I just keep getting values that are a little bit off. If you'll give me a second, let me take a look at this issue, and I'll get back to you once I have a good answer to it. Yeah, so the issue was down here. This took me an annoying amount of time to figure out, but I had x0 and f0 indented into this if loop, so they were only running after a break, but of course as soon as a break happens, it breaks out of this for loop and just returns x1. So these codes weren't running, And so I was returning the last value I found before finishing the iteration, essentially, or before the tolerance was equal to 0. So if I go ahead and do that and run the Newton's method, I can run the Newton's method again, and now I will get the array I am looking for evaluated at 0.2, or not evaluated, but it's saying that for the x, y defined earlier, it's saying, the Newton's method is saying that for my initial guess of 0.3, I find a root at 0.2, which, if you look at this, yep, that looks about correct. So, with showing that's consistent with the function, I have finished part 2a. I explained and coded the Secant and Newton methods for finding the root of a scalar one-dimensional function. With that, I will end things off here for today. I hope you enjoyed the video, and I hope you learned something, and I hope you have a wonderful day. Bye-bye.